Hello everyone. So in this video we're actually going to look at Stoke's theorem. Alright, and before we move on to Stoke's theorem, by now everyone would have been very familiar with this operator here, which is the gradient, or what we call as the nabla in short. Just to refresh and to recall whatever that we've learned. Okay, when we have this nabla or the gradient multiplied by a scalar, what we actually get, say f is a scalar function, so we actually get what we call a gradient of a scalar field. This is pretty much straightforward. In fact, in the previous video we have actually looked at this, where you actually find conservative vector field, if you still remember. And say when we have another situation would be when your nabla or your gradient is multiplied by vector, alright, using the dot product. What do we get then? So if you recall, if we have this nabla here with the dot product of another vector field, remember saying this? This is actually what we have been doing in the divergence theorem. As you can see, there's the nabla dot the f, which is the vector field. Alright, and also we still also have another one where you still have nabla multiplied by vector, and instead of, I'm just going to write this down as vector again, but instead of using dot product, we're actually using cross product. Okay, and then the denotation will go with this x here being the cross product, and this is actually the curl of our function f. Alright, so I hope that with this recap everyone is pretty clear about whatever that we have been doing so far. So you can see that all the previous chapters also have quite a relation to whatever topics that we have come so far. Anyway, so let's start. I'm just going to scroll this up because today I want to actually talk about Stoke's theorem. So actually Stoke's theorem here actually came from an Irish guy, and he's actually a mathematical physicist. His name is Sir George Stokes. And just a question on when do we actually use Stokes' theorem? Alright, and it has something related to our line integral as well. So if you recall from the previous topic, we actually looked at line integral with a given curve of a certain function and all. But how different it is for Stokes' theorem is that we usually use this when our line integral will be quite unpleasant to deal with. So in other words, it's kind of slightly more complicated and all that. But anyway, let's see what Stokes' theorem tells us about. It is now saying that the double integral, so this is what Stokes' theorem is about. It says that the double integral, or in this case the surface integral of my del cross f dot n cap dA is actually equivalent to the line integral of my vector field, which in this case I'll just write this as f dot t ds. So if we are going to visualize this, so we can have something of the same object here. So take that these two objects are similar. So what happens, or what can be visualized from this left hand side here, basically just means that, okay, the surface integral of, and I'm actually writing and drawing this circulation mode, alright, because my curl here actually indicates this, and with the dot product of my n cap is basically my unit vector normal, alright, with respect to my surface integral of my dA, therefore the double integral over here. So what it's saying is that the curl of my f with the dot product of my n cap dA is exactly the same as this one here. which is the circulation, right? Remember line integral of a closed path? That is what we call a circulation. Okay, and this will then be indicated by an S, and yeah, so this C here is just to indicate the curve that's around it. Alright, so basically what it is telling here is that this left hand side is actually equal to my right hand side, and at any given point of time, if there is any object that is quite difficult to calculate and all that, you can also consider Stoke's theorem. And if you can see that on the left hand side here, it kind of just depends on the boundary line. It doesn't really matter, it doesn't really care about the particular surface that is being used. Okay, and then but I think we can just look at example and all that after this so that you're more clear with this. So that's all about Stoke's theorem. Another thing that we would like to look at, so if you want to just look at how we actually perform Stoke's theorem in an example and all that, you can just pause the video right now and actually look at the next video. Actually, the next one that I'm going to talk about is Laplace. Okay, so Laplace, you will see that it's going to be quite similar to something what we call as the Poisson equation. So I'll just scroll this up a little bit. Okay, let's talk a little bit about Laplace. We do know that electric field E is related to our rho here being our charge density, yeah, by our divergence theorem. Agree? So this is something that you would have seen in the second topic of the second half when we learned divergence theorem earlier. So we do know that the nabla dot E bar is also equivalent to my rho over epsilon naught. And if you recall, this equation here is what we have learned in Gauss' law earlier. And now, we also do know that electric field is related to potential by gradient denoted by nabla, right? And how is it related? My E bar is actually also equivalent to my negative del of my V being my potential. And therefore, based on this itself, we can see that our potential is related to our charge density rho by, so if you look at what I'm going to put here, right, we do know that our E is also equivalent to our negative nabla of V. So if I'm going to replace these two with and put it into the first equation on top here, what we will have is nabla dot nabla V, which is also equivalent to nabla square V equals to negative rho over infinity. Over epsilon naught. So see that the negative has been pushed to this side here, just for simplicity purpose. And this formula that you see here is actually what we know as the Poisson equation. And Poisson equation is very, very much related to Laplace equation. And how is it related? Basically, what it tells us is that when you have zero charge density in the region, that will give us 0, isn't it? So if I replace my rho, which is my charge density equals to 0, into the equation in my Poisson equation here, so what I will get is nabla square V equals to 0. And this is then what we know as Laplace equation. But by now, everything would seem to be quite simple to you, because by now I hope everyone is pretty clear about the operational of our nabla, how to differentiate the dot product and the cross product and so on and all that. So this would be the summary for the topic here. Alright, do click on the next video to look at example if you need to. Happy studying!